Hi, I'm Victor. Today, I'm going to do a demonstration on our project Police Radar Gun, showing how we connect our hardware components. These are the components we use. Firstly, we connect the SMA cable to the signal generator, then the other end of the cable to the input port of the splitter. The purpose of the splitter is to produce two identical signals. Next, one output port from the splitter is connected to the power amplifier. This is to boost up the signal strength, which is then connected to the first horn attenuator, acting like a medium to transmit the signal. A diode from the power supply is connected to start up the power amplifier. Next, we connect two SMA to coaxial adapter to the mixer. The other output port from the splitter is connected to one input port of the mixer. Then the other input port is connected with a 10 dBm attenuator. The purpose of the attenuator is to attenuate the amplitude of the receiving signal. At the other end of the attenuator, we connect to the RF output of the low noise amplifier. This amplifier is to reduce the effect of noise and amplifies the signal strength. The second horn attenuator acts as a medium to receive the reflected signal. It is connected to the RF input of the low noise amplifier. A 12 volt from the power supply is connected to start up the low noise amplifier. Next, we connect the output port of the mixer using a coaxial cable to channel 0 port of the Elvis. The purpose of the mixer will take the difference of the two signals, which shows the Doppler frequency, and send the resultant signal through port 0 to the Elvis. The Elvis will pick up the signal, and data analysis of the signal is done using LabVIEW software. After all the connections, we set up the signal generator. Frequency to 1.7 GHz. And amplitude to 15 dBm, and on it. Then we set up the power supply and on it.
Hi everyone, today we are going to learn how to implement Police Radar gun system using LabVIEW software. Let's begin with the DAQ assistant that you can see on the screen. DAQ assistant is used to convert the signal from analog to digital. Once we have the digital signal coming out of the DAQ assistant, we sample it using the sampler, and then the signal is fed to the waveform graph to display. And at the same time, we also fed the signal into the FFT power spectrum in order to get the frequency domain waveform from the time domain. Once we obtain the frequency domain graph, we unbundle the graph in order to get the magnitude of each component of the array. Once we have all the magnitudes, we display it with respect to frequency again using the waveform graph. Okay, once we display the FFT, we then feed the signal into the replace array subset function of LabVIEW. Basically, this function helps us to set any value of the array to an integer. So we use this replace array subset function to reduce the first 4 elements of the FFT graph to 0. Why we are doing this is because we need this amplitude to be 0 in order for a better detection of the Doppler. Doppler frequency amplitude is always lower than the first 4 frequency of the FFT graph. So this helps us to better detect the Doppler frequency. Okay, once we nullify the first 4 frequencies from the FFT graph, we again display the graph, which you can see on FFT2. Okay, finally we need to know the Doppler frequency of from the graph. So in order to obtain the Doppler frequency, we pinpoint to the maximum amplitude by using the maximum and minimum value array function, which you can see on the screen. This minimum and maximum value function gives out the maximum value of the array and at what frequency the value occurs. So the frequency at which the maximum value occurs is the Doppler frequency. Then we display the Doppler frequency, which you can see on the graph FD. Once we have the Doppler frequency, we just need to simply apply the Doppler effect formula, which consists of carrier frequency, Doppler frequency, and speed of light. Then the big box is a condition set to calculate the velocity of the vehicle. Basically, in the box we set the condition as 6e minus 8. This condition is the maximum value a noise signal can reach. So we do not calculate the velocity unless and until the noise signal is below 6e to the power minus 8. So the velocity will only be calculated if the Doppler frequency is more than 6e to the power minus 8. If not, the velocity will simply be displayed as 0, which you can see on the graph. Then the velocity is displayed in terms of meter per second using this indicator on the screen, and in terms of kilometer per hour using this indicator, which you can see on the screen. Thank you for your time. Hope you learn something from the video.